Question 1. The evaluation methodology shows a comparative analysis of two neural network implementations for a fraud detection task. One implementation utilizes sigmoid activation functions throughout, a basic gradient descent optimizer, and a standard mean-squared error loss function. The second implementation employs ReLU activation functions in hidden layers, ATOM as the optimizer, and a cross-entropy loss function, with backpropagation applied correctly in both. Considering the typical challenges in training deep neural networks and the nature of fraud detection, which approach is more likely to yield a robust and efficient model, and why? Option A. The first implementation is superior because basic gradient descent is easier to understand and implement, making it less prone to errors, and sigmoid functions are well established for their interpretability. Option B. The second implementation is superior because ReLU mitigates the vanishing gradient problem common with sigmoid in deeper networks. ATOM provides more efficient convergence than basic gradient descent, and cross-entropy is generally more suitable for classification tasks than mean-squared error. Option C. The first implementation is superior because sigmoid activation functions provide a smoother gradient, which can lead to more stable training, and mean-squared error is a universally applicable loss function for regression and classification. Option D. The second implementation is superior because it uses a more complex architecture, which is always better for fraud detection, and ATOM is a more computationally intensive optimizer, ensuring thoroughness. The correct answer is B. The second implementation is superior because ReLU mitigates the vanishing gradient problem common with sigmoid in deeper networks. ATOM provides more efficient convergence than basic gradient descent, and cross-entropy is generally more suitable for classification tasks than mean-squared error. Explanation. The evaluation methodology shows a common challenge in data science projects, selecting the most appropriate neural network architecture and training strategy for a given problem. This scenario is professionally challenging because the choice of activation functions, backpropagation implementation, and optimization algorithms directly impacts model performance, interpretability, and computational efficiency. Misjudgments can lead to suboptimal results, wasted resources, and potentially non-compliant models if regulatory requirements for model fairness or explainability are not met. Careful judgment is required to balance theoretical understanding with practical application. The correct approach represents best professional practice because it demonstrates a nuanced understanding of how different components of a neural network interact and how to select them based on the problem's characteristics and desired outcomes. Specifically, choosing ReLU for its computational efficiency and ability to mitigate vanishing gradients, implementing backpropagation correctly to enable learning, and selecting ATOM for its adaptive learning rates and robustness in optimization are all standard, effective practices. This approach aligns with professional standards for building performant and reliable machine learning models, which indirectly supports compliance with any regulations requiring accurate and efficient data processing. An incorrect approach that relies solely on sigmoid activation functions for all layers would be professionally unacceptable due to the vanishing gradient problem, which can severely hinder learning in deep networks. This failure to adapt the activation function to the network's depth can lead to a model that does not converge or performs poorly, potentially violating implicit or explicit requirements for model efficacy. Another incorrect approach that uses a basic gradient descent without momentum or adaptive learning rates might be too slow to converge or get stuck in local minima, leading to inefficient resource utilization and potentially a model that fails to meet performance benchmarks, which could be a concern in regulated environments where timely and accurate predictions are crucial. An approach that incorrectly implements backpropagation, leading to inaccurate gradient calculations, would fundamentally break the learning process, resulting in a model that is not fit for purpose and could lead to significant downstream issues, potentially breaching data governance or accuracy standards. Professionals should employ a decision-making framework that involves understanding the problem domain, the characteristics of the data, and the specific objectives of the model. This includes researching and understanding the trade-offs of different activation functions, e.g., ReLU for speed and avoiding vanishing gradients, sigmoid for binary classification outputs, the principles of backpropagation for effective weight updates, and the advantages of modern optimizers like ATOM over basic gradient descent. When faced with choices, professionals should consider empirical testing and validation to confirm their selections, ensuring that the chosen methods are not only theoretically sound, but also practically effective for the specific task at hand, thereby upholding professional integrity and ensuring compliance with any applicable data science standards. Question 2. The control framework reveals that a data scientist is tasked with developing a predictive model for loan default risk. To ensure the model's reliability and fairness, the data scientist must select appropriate techniques for evaluating model performance and tuning its parameters. Considering the regulatory environment that emphasizes fair lending practices and robust model validation, which of the following approaches best aligns with these requirements? Option A. Relying solely on a simple k-fold cross-validation without stratification and employing a basic random search for hyperparameter tuning while omitting regularization. Option B. Using a single train test split for initial performance assessment and then performing an extensive grid search for hyperparameter optimization without considering regularization. Option C. Implementing a single train test split and applying L1 regularization, with hyperparameter tuning performed through a manual, iterative process based on intuition. Option D. Employing stratified k-fold cross-validation for performance evaluation, utilizing Bayesian optimization for hyperparameter tuning, and applying L1 and L2 regularization to the model. The correct answer is D. Employing stratified k-fold cross-validation for performance evaluation, utilizing Bayesian optimization for hyperparameter tuning, and applying L1 and L2 regularization to the model. Explanation. The control framework reveals a common challenge in data science projects, ensuring model robustness and generalizability while adhering to regulatory expectations for transparency and fairness. The scenario is professionally challenging because the data scientist must select and tune a model that not only performs well on unseen data, but also demonstrably avoids bias, a critical concern in regulated industries. The pressure to deliver a high-performing model quickly can tempt shortcuts that compromise these essential controls. Correct approach represents best professional practice because it systematically evaluates model performance across diverse data subsets, directly addressing the risk of overfitting and ensuring the model's reliability in real-world varied conditions. Stratified k-fold cross-validation is particularly crucial when dealing with imbalanced datasets or when specific subgroups within the data are of regulatory interest, e.g., protected classes in credit scoring. Hyperparameter optimization, when conducted using methods like Bayesian optimization, is more efficient and less prone to overfitting than exhaustive grid search, allowing for a more thorough exploration of the hyperparameter space without excessive computational cost. Regularization techniques, such as L1 and L2, are fundamental for preventing overfitting by penalizing model complexity, thereby improving generalization. This combination of techniques aligns with regulatory expectations for model validation, risk management, and the prevention of discriminatory outcomes, as often mandated by frameworks like the U.S. Equal Credit Opportunity Act (ECOA) or similar data privacy and fairness regulations. An incorrect approach that relies solely on a single train test split without cross-validation is professionally unacceptable due to significant regulatory and ethical failures. This method provides a single, potentially misleading, performance metric and offers no insight into how the model will perform on different data distributions. It fails to meet the standard for robust model validation, increasing the risk of deploying a model that performs poorly or unfairly in production, which could lead to violations of fair lending laws or data privacy regulations. Another incorrect approach that uses grid search without considering computational feasibility or the risk of overfitting to the validation folds is also problematic. While grid search explores the hyperparameter space, an unconstrained grid search can be computationally prohibitive and may lead to selecting hyperparameters that perform exceptionally well on the specific validation folds but do not generalize. This lack of efficiency and potential for overfitting can indirectly lead to regulatory issues if the model's performance is not reliably validated. Finally, an approach that neglects regularization techniques entirely, even when faced with complex models or limited data, is professionally deficient. This omission increases the likelihood of overfitting, where the model learns the training data too well, including its noise, and fails to generalize to new data. Overfitting can lead to unpredictable and potentially unfair outcomes, which can trigger regulatory scrutiny and penalties, especially in sensitive applications like loan applications or insurance underwriting. The professional decision-making process for similar situations should involve a risk-based approach. First, understand the regulatory landscape and potential impacts of model failure, e.g., fairness, privacy, accuracy. Second, select validation strategies, like stratified cross-validation, that are appropriate for the data characteristics and regulatory concerns. Third, choose hyperparameter optimization methods that balance thoroughness with efficiency and the risk of overfitting. Fourth, incorporate regularization techniques as a standard practice to enhance model robustness. Finally, document all steps, justifications, and performance metrics thoroughly to demonstrate compliance and due diligence. Question 3. Operational review demonstrates that the data science team is encountering inefficiencies in processing diverse data files, e.g., CSV, JSON, plain text logs, arriving from various sources. The current ad hoc scripting approach is becoming difficult to maintain and scale. The team needs a more structured and object-oriented Python solution to parse, validate, and store data from these different formats. The solution should be easily extensible to accommodate new file types in the future without significant refactoring. Which of the following Python implementation strategies best addresses these requirements? Option A. Implement a single, large Python script with a series of nested if-else statements to detect the file type, and then use a generic dictionary to store all parsed data, regardless of its original structure, accessing elements by index. Option B. Develop a solution that exclusively uses immutable tuples to represent all data, even for dynamic or structured information, and relies on string manipulation for parsing and data extraction. Option C. Design a base-class data processor with abstract methods for parsing and validation. Create specific subclasses like CSV processor, JSON processor, and text log processor that inherit from data processor, and implement the abstract methods using appropriate data structures like dictionaries for structured data and lists for sequential records. Utilize functions within these classes for specific processing steps. Option D. Create a set of standalone functions, each dedicated to processing a specific file type, and store all processed data in a global list of tuples, where each tuple represents a record. The correct answer is C. Design a base-class data processor with abstract methods for parsing and validation. Create specific subclasses like CSV processor, JSON processor, and text log processor that inherit from data processor, and implement the abstract methods using appropriate data structures like dictionaries for structured data and lists for sequential records. Utilize functions within these classes for specific processing steps. Explanation. Scenario analysis. This scenario presents a common challenge in data science projects: managing and processing diverse data types efficiently and robustly. The need to handle potentially large datasets, ensure data integrity, and implement flexible processing logic requires a strong understanding of Python's core data structures and programming paradigms. The professional challenge lies in selecting the most appropriate tools and techniques to meet performance, maintainability, and scalability requirements within the constraints of a typical data science workflow. Missteps can lead to inefficient code, difficult debugging, and potential data corruption, impacting project timelines and the reliability of insights. Correct approach analysis. The correct approach leverages Python's built-in data structures and object-oriented features to create a modular and extensible solution. Using a class to encapsulate the data processing logic for each file type allows for clear separation of concerns and promotes code reusability. Inheritance can be employed to define a base data processor class with common methods, and then specialized subclasses, e.g., CSV processor, JSON processor, can override or extend these methods to handle specific parsing and validation logic. Dictionaries are ideal for storing parsed data from structured formats like JSON or key-value pairs, while lists are suitable for ordered sequences of records. Functions within these classes encapsulate specific operations, making the code readable and testable. This object-oriented design, combined with appropriate data structures, ensures that the system can easily accommodate new file formats in the future without extensive code refactoring, aligning with best practices for maintainable and scalable software development in a professional data science environment. Incorrect approaches analysis. An approach that relies solely on a series of nested if-else statements and procedural functions to handle each file type is professionally problematic. This leads to a monolithic and difficult-to-maintain codebase. If a new file format is introduced, the entire processing logic would need to be modified, increasing the risk of introducing bugs. This lack of modularity violates principles of good software engineering, making it harder to debug and test individual components. Ethically, it can lead to a higher chance of errors in data processing, potentially resulting in flawed analyses and decisions based on incorrect data. Another incorrect approach might involve using a single, overly complex dictionary to store all data, regardless of its structure or origin. Dictionaries are versatile. Attempting to force all data into a single, unstructured dictionary can lead to significant ambiguity, making it difficult to retrieve specific pieces of information and increasing the likelihood of data type mismatches or accidental overwrites. This approach lacks the clarity and organization provided by specialized data structures and object-oriented design, hindering maintainability and increasing the potential for errors. It fails to adhere to professional standards of data organization and management. A third incorrect approach could involve using tuples exclusively for all data storage, even for mutable data or when key-value associations are crucial. Tuples are immutable, which can be beneficial for ensuring data integrity in certain contexts, but they are not suitable for representing dynamic datasets or structured records, where elements need to be accessed by name or modified. This inflexibility would lead to convoluted workarounds and inefficient data manipulation, making the code harder to understand and debug. It represents a failure to select the most appropriate tool for the job, a key aspect of professional data handling. Professional reasoning. Professionals should approach this challenge by first identifying the core requirements, handling multiple data formats, ensuring data integrity, and enabling future extensibility. The decision-making process should prioritize modularity, readability, and maintainability. This involves evaluating Python's data structures and programming paradigms against these requirements. Object-oriented programming, with its emphasis on classes and inheritance, provides a robust framework for managing diverse processing logic. Selecting the right data structure, lists for ordered sequences, dictionaries for key-value pairs, sets for unique elements, for the specific data being processed is crucial for efficiency and clarity. When faced with similar situations, professionals should always consider the long-term implications of their design choices, aiming for solutions that are not only functional, but also easy to understand, debug, and extend by themselves and their colleagues. This proactive approach minimizes technical debt and ensures the reliability of data-driven insights. Question 4. Stakeholder feedback indicates an urgent need to incorporate a new data visualization feature into the production environment within the next 24 hours. The data scientist has developed the feature and believes it is ready for deployment. To meet the deadline, the data scientist is considering bypassing the standard branching and merging workflow for this specific change. Option A. Directly commit the new visualization code to the main branch to expedite deployment. Option B. Create a new feature branch for the visualization code, develop and test the feature on this branch, and then submit a pull request for review and merging into the main branch. Option C. Merge the new visualization code directly into the main branch without a formal code review. Option D. Create a separate, unlinked repository to house the new visualization code and deploy it independently. The correct answer is B. Create a new feature branch for the visualization code, develop and test the feature on this branch, and then submit a pull request for review and merging into the main branch. Explanation. This scenario presents a professional challenge due to the inherent tension between rapid development and maintaining code integrity and auditability, especially within a regulated environment. The need to incorporate stakeholder feedback quickly can lead to pressure to bypass established version control protocols, risking the introduction of errors, loss of traceability, and potential noncompliance with data governance policies. Careful judgment is required to balance agility with robust development practices. The correct approach represents best professional practice because it prioritizes a structured and auditable workflow. By creating a dedicated feature branch for the stakeholder-requested changes, the data scientist ensures that the main development line, e.g., main or master, remains stable and production-ready. This branching strategy allows for isolated development, testing, and review of the new features without impacting existing functionality. Subsequent merging of the feature branch into the main line, after thorough code review and testing, ensures that only validated and integrated changes are deployed. This process directly supports regulatory requirements for traceability, accountability, and quality assurance in data science projects, as it provides a clear history of all code modifications, who made them, and when. An incorrect approach of directly committing changes to the main branch without proper branching or review is professionally unacceptable. This bypasses the established version control workflow, leading to a loss of granular history and making it difficult to revert specific changes if issues arise. Ethically, it undermines team collaboration and transparency. From a regulatory perspective, it creates significant auditability gaps. If a bug is introduced, it becomes challenging to pinpoint the exact commit responsible, hindering incident response and potentially violating data integrity or security regulations that mandate clear audit trails. Another incorrect approach of creating a separate, unlinked repository for the stakeholder feedback is also professionally unacceptable. This isolates the changes, making them difficult to integrate back into the main project and creating a fragmented codebase. It violates the principles of centralized version control, which are crucial for collaborative development and maintaining a single source of truth. This fragmentation can lead to inconsistencies, duplicated effort, and a lack of a unified project history, all of which are detrimental to regulatory compliance and project maintainability. A third incorrect approach of merging the stakeholder feedback directly into the main branch without a code review is professionally risky. While it might seem faster, it skips a critical quality assurance step. Code reviews are essential for catching potential bugs, security vulnerabilities, and deviations from best practices. Failing to conduct reviews increases the likelihood of introducing errors into the production environment, which can have significant consequences, including financial loss, reputational damage, and regulatory penalties if the errors impact data accuracy or system reliability. This approach neglects the professional responsibility to ensure the quality and robustness of the code. The professional decision-making process for similar situations should involve 1. Understanding the immediate request and its potential impact. 2. Evaluating the request against established version control policies and best practices. 3. Prioritizing a structured workflow, e.g., branching, that balances speed with integrity. 4. Communicating the chosen approach to stakeholders, explaining the rationale for maintaining robust development processes. 5. Ensuring all changes are thoroughly tested and reviewed before integration. Question 5. Risk assessment procedures indicate that a large retail chain is experiencing challenges in optimizing product placement and promotional strategies due to an inability to efficiently identify frequently co-purchased items across millions of daily transactions. The data science team needs to implement a robust association rule mining solution to uncover these relationships. Considering the scale of the data and the need for actionable insights, which of the following approaches best addresses these requirements? Option A. Focus solely on generating rules with the highest possible confidence, irrespective of support or lift, to ensure that the identified co-purchases are definitively linked. Option B. Implement the a priori algorithm, focusing on generating a very large number of association rules with high confidence, and then manually review the most frequent ones for potential business value. Option C. Utilize the FP growth algorithm, carefully tuning support and confidence thresholds to identify rules with significant lift, thereby uncovering non-obvious but valuable co-purchase patterns. Option D. Employ a naive approach of calculating pairwise co-occurrence frequencies for all item pairs without using a formal association rule mining algorithm, and then filter based on a fixed, low support threshold. The correct answer is B. Implement the a priori algorithm, focusing on generating a very large number of association rules with high confidence, and then manually review the most frequent ones for potential business value. Explanation. Scenario analysis. This scenario presents a common challenge in data science where the interpretation and application of association rule mining algorithms are critical for business strategy. The challenge lies in selecting the most appropriate algorithm and understanding its implications for actionable insights, especially when dealing with potentially sensitive customer data. Misinterpreting the results or choosing an inefficient algorithm can lead to flawed business decisions, wasted resources, and potentially regulatory noncompliance if data privacy is not adequately considered. The need for a robust and scalable solution is paramount, particularly in large datasets typical of retail environments. Correct approach analysis. The correct approach involves leveraging the FP growth algorithm for its efficiency in handling large datasets by avoiding repeated scans of the transaction database. FP growth constructs a compact FP tree representation of the database, from which association rules can be mined more quickly than with apiary, which requires multiple passes. This efficiency is crucial for timely business decision-making and resource optimization, aligning with the professional responsibility to deliver effective and timely solutions. Furthermore, understanding the metrics of support, confidence, and lift is essential for interpreting the strength and significance of the discovered rules, ensuring that insights are actionable and not merely coincidental. This approach prioritizes both algorithmic efficacy and the practical interpretation of results, leading to sound business strategies. Incorrect approach is analysis. An approach that solely relies on the apiary algorithm without considering its performance limitations on large datasets is professionally suboptimal. While apiary is foundational, its iterative candidate generation and testing can become computationally expensive, leading to delays in insight generation and potentially higher infrastructure costs. This inefficiency can hinder timely business responses. Another incorrect approach would be to focus exclusively on generating a high volume of rules without a clear understanding of their business value, as indicated by metrics like lift. This can lead to information overload and the identification of trivial or spurious correlations, wasting analytical effort and potentially misleading decision-makers. It fails to demonstrate a deep understanding of how to translate data insights into strategic advantage. Finally, an approach that neglects the interpretation of support, confidence, and lift, or misapplies these metrics, is fundamentally flawed. For instance, a rule with high confidence but low lift might indicate a common co-occurrence that isn't particularly insightful for driving new business actions. This demonstrates a lack of critical evaluation of the discovered associations, leading to potentially ineffective or even detrimental business strategies. Professional reasoning. Professionals should approach association rule mining by first understanding the scale and characteristics of the dataset. For large datasets, FP growth is generally preferred due to its performance advantages. Subsequently, a thorough evaluation of the generated rules using support, confidence, and lift is critical. This involves setting appropriate thresholds for these metrics based on business objectives and domain knowledge to identify truly valuable and actionable insights. The decision-making process should prioritize algorithms that offer both computational efficiency and the ability to derive meaningful, interpretable rules that can drive strategic business decisions, while always being mindful of the potential for data privacy implications. Question 6. Process analysis reveals that a data scientist has developed a predictive model for customer churn. While the model achieves a statistically significant result, the underlying data exhibits considerable noise and potential for selection bias due to the sampling methodology. Stakeholders are eager for an immediate deployment recommendation. Which of the following approaches best balances statistical integrity with practical business needs? Option A. Focus solely on the model's ability to identify a small but statistically significant segment of high-risk customers, recommending targeted interventions for this segment, without mentioning the broader predictive capabilities or the limitations of the model for the general customer base. Option B. Recommend immediate full-scale deployment of the model, emphasizing the statistically significant p-value as proof of its effectiveness, and deferring any discussion of data limitations until after the initial deployment phase. Option C. Advise stakeholders that the model is not yet ready for deployment due to inherent data limitations, and suggest a significant, time-consuming data collection and cleaning effort before any recommendations can be made, even if it means delaying insights for an extended period. Option D. Present the model's predictions with a clear disclaimer about the potential impact of data noise and sampling bias on the accuracy and generalizability of the results, recommending a phased rollout with ongoing monitoring and validation. The correct answer is D. Present the model's predictions with a clear disclaimer about the potential impact of data noise and sampling bias on the accuracy and generalizability of the results, recommending a phased rollout with ongoing monitoring and validation. Explanation. Scenario analysis. This scenario is professionally challenging because it requires a data scientist to balance the pursuit of statistical rigor with the practical constraints of a business environment, specifically the need for timely insights. The pressure to deliver results quickly can lead to shortcuts that compromise the validity of statistical findings, potentially leading to flawed business decisions. The data scientist must navigate the ethical imperative to present accurate and reliable information, while also meeting stakeholder expectations for speed. This requires a nuanced understanding of statistical principles and their implications in a real-world context, where perfect data and infinite time are rarely available. Correct approach analysis. The correct approach represents best professional practice because it acknowledges the inherent uncertainties in statistical modeling and prioritizes transparency and a measured interpretation of results. By explicitly stating the limitations of the model and the potential for bias, the data scientist upholds the ethical obligation to provide an honest and complete assessment of the findings. This approach aligns with professional guidelines that emphasize the importance of clearly communicating assumptions, limitations, and the degree of confidence in any statistical conclusions. It allows stakeholders to make informed decisions, understanding the context and potential risks associated with the insights derived from the data. This fosters trust and ensures that the data science function is perceived as a reliable source of information, rather than a black box that generates potentially misleading outputs. Incorrect approaches analysis. One incorrect approach involves presenting the model's output as definitive truth without acknowledging potential biases or limitations. This is professionally unacceptable because it misrepresents the nature of statistical inference. Statistical models are approximations of reality, and their outputs are subject to error and bias, especially when dealing with real-world imperfect data. Failing to disclose these limitations can lead to overconfidence in the results, resulting in poor strategic decisions based on an incomplete or inaccurate understanding of the underlying phenomena. This violates the ethical principle of honesty and integrity in professional practice. Another incorrect approach is to overemphasize the statistical significance of minor findings, while downplaying the practical implications or the potential for spurious correlations. This can occur when a data scientist focuses solely on p-values without considering effect sizes or the broader business context. Professionally, this is problematic as it can lead to misallocation of resources towards initiatives that have statistically detectable but practically insignificant impacts. It also risks creating a perception that statistical significance is the sole determinant of value, ignoring the critical need for actionable and impactful insights. This approach can be seen as misleading stakeholders by presenting noise as signal. A third incorrect approach is to delay the delivery of insights indefinitely in pursuit of a theoretically perfect model, even when a reasonably robust model could provide valuable, albeit imperfect, guidance. While striving for accuracy is important, an inability to deliver timely insights can render them obsolete or less impactful. Professionally, this demonstrates a lack of understanding of the business cycle and the need for pragmatic solutions. It can also be interpreted as an avoidance of responsibility or an inability to manage project scope and deliverables effectively. This approach fails to meet the professional obligation to contribute to the organization's objectives in a timely manner. Professional reasoning. Professionals should adopt a decision-making framework that prioritizes transparency, context, and pragmatic application of statistical knowledge. This involves 1. Understanding the business objective and the acceptable level of risk for decision-making. 2. Rigorously applying statistical methods while being acutely aware of their assumptions and limitations. 3. Clearly communicating findings, including confidence intervals, potential biases, and the practical implications of the results, tailored to the audience's understanding. 4. Iteratively refining models and insights based on feedback and evolving business needs, rather than seeking an unattainable state of perfection. 5. Maintaining a commitment to ethical conduct by ensuring that all analyses and presentations are honest, accurate, and free from manipulation. Question 7. The efficiency study reveals that a financial institution needs to predict loan default risk with high accuracy to minimize financial losses. The dataset is large and contains complex interactions between various financial indicators. The institution also requires a degree of transparency in the model's decision-making process for regulatory compliance and customer communication. Which ensemble method would be the most appropriate choice, considering both predictive performance and the need for some level of interpretability? Option A, bagging e.g. random forest. Option B, gradient boosting machines e.g. XGBoost Lite GBM. Option C, stacking. Option D, ADA boost. Correct answer is B, gradient boosting machines e.g. XGBoost Lite GBM. Explanation. Scenario analysis. This scenario presents a common challenge in data science where multiple ensemble methods are available, each with distinct strengths and weaknesses. The professional challenge lies in selecting the most appropriate method for a given business problem, considering not only predictive performance but also interpretability, computational resources, and potential biases. The need for careful judgment arises from the potential impact of model choice on business decisions, regulatory compliance, and ethical considerations, especially in sensitive domains. Correct approach analysis. The correct approach involves a systematic evaluation of ensemble methods against the specific requirements of the problem. For a scenario demanding high accuracy and robustness against overfitting, gradient boosting, or XGBoost, are often superior due to their sequential learning process that corrects errors from previous models. XGBoost, in particular, offers advanced regularization techniques and parallel processing capabilities, making it a strong contender for complex datasets. This aligns with professional best practices by prioritizing a model that demonstrably achieves superior predictive power while managing complexity, thereby leading to more reliable insights and business outcomes. Adherence to data science best practices, which implicitly guide ethical and responsible AI deployment, is paramount. Incorrect approach is analysis. Choosing XGBoost without considering the dataset's characteristics or the presence of outliers would be a regulatory/ethical failure. XGBoost is sensitive to noisy data and outliers, which can lead to biased models and potentially unfair or discriminatory outcomes if the data reflects societal biases. This violates the principle of fairness and accuracy in AI. Selecting stacking without a clear understanding of the base learner's diversity and the meta-learner's complexity would be a professional failure. While stacking can achieve high accuracy, it often sacrifices interpretability, making it difficult to explain model predictions. In regulated industries, a lack of explainability can hinder compliance with audit requirements and consumer protection laws. Opting for bagging, like random forest, solely because it is a well-known ensemble method, without evaluating if its inherent variance reduction is the primary need, would be a missed opportunity for optimization. While generally robust, it might not achieve the same level of accuracy as boosting methods on certain datasets where bias reduction is more critical. This represents a failure to apply the most effective tool for the job, potentially leading to suboptimal business decisions. Professional reasoning. Professionals should employ a decision-making framework that begins with a thorough understanding of the business problem, data characteristics, and desired outcomes. This includes defining success metrics, considering interpretability needs, and assessing computational constraints. A comparative analysis of candidate ensemble methods, often involving cross-validation and rigorous performance evaluation, is crucial. The choice should be justified by empirical evidence and aligned with ethical principles of fairness, transparency, and accountability. When in doubt, prioritizing methods that offer a balance between performance and interpretability, or those with built-in mechanisms for bias detection and mitigation, is a sound professional strategy. Question 8. The control framework reveals that a data science team is tasked with developing a predictive model. The initial data exploration involves loading large datasets, cleaning and transforming the data, performing statistical analysis, and visualizing key trends. The modeling phase requires implementing various machine learning algorithms, and the final output needs to be presented with clear and informative visualizations. Which of the following approaches best aligns with professional best practices for library selection in this scenario? Option A. Employ a single highly specialized third-party library that claims to handle all aspects of data science from data ingestion to visualization, even if it has a smaller community and less extensive documentation. Option B. Rely solely on Python's built-in data structures and functions for all data loading, manipulation, and analysis tasks to minimize external dependencies. Option C. Use basic Python lists and loops for all data manipulation and analysis, and implement custom algorithms for machine learning and visualization to ensure complete control over the process. Option D. Utilize NumPy for numerical operations, Pandas for data manipulation and analysis, scikit-learn for machine learning algorithms, and matplotlib/seaborn for data visualization, leveraging SciPy for any advanced scientific computing needs. The correct answer is D. Utilize NumPy for numerical operations, Pandas for data manipulation and analysis, scikit-learn for machine learning algorithms, and matplotlib/Seaborn for data visualization, leveraging SciPy for any advanced scientific computing needs. Explanation. The scenario presents a common challenge in data science projects, selecting appropriate libraries for specific tasks while adhering to best practices and potential implicit organizational guidelines for efficiency and maintainability. The professional challenge lies in balancing the immediate needs of a project with long-term considerations like code readability, performance, and the ability for other team members to understand and contribute. Careful judgment is required to avoid over-engineering or underutilizing available tools. The correct approach emphasizes using libraries that are purpose-built for the task at hand, promoting clarity and efficiency. For numerical computations, NumPy is the standard. For data manipulation and analysis, Pandas offers robust and intuitive data structures and operations. For machine learning, scikit-learn is the industry standard, providing a comprehensive suite of algorithms and tools. For visualization, Matplotlib and Seaborn are widely adopted and offer powerful capabilities. SciPy is valuable for more advanced scientific and technical computing tasks. This approach aligns with best professional practices by leveraging specialized tools, leading to more readable, maintainable, and performant code. It also implicitly supports collaboration, as team members are likely familiar with these widely adopted libraries. An incorrect approach might involve attempting to perform all data manipulation tasks using only basic Python lists and loops. This would be inefficient, error-prone, and significantly harder to read and debug, failing to leverage the optimized functionalities of libraries like Pandas. Ethically, it could be seen as a failure to deliver a project with due diligence if more efficient and reliable tools were readily available and known. Another incorrect approach could be to use a less common or specialized library for a task that is well covered by a standard library, such as using a general-purpose plotting library for complex statistical visualizations, when Seaborn is specifically designed for such tasks. This could lead to increased development time, potential compatibility issues, and a steeper learning curve for collaborators, representing a failure in professional efficiency and knowledge sharing. A third incorrect approach might be to exclusively rely on a single library for all tasks, even when other libraries offer superior functionality for specific subtasks. For example, attempting to perform complex statistical analyses solely within Pandas, without utilizing SciPy's specialized modules, would be a suboptimal choice, potentially leading to less accurate or less efficient results, and demonstrating a lack of comprehensive understanding of the available toolset. The professional decision-making process should involve understanding the core requirements of the data science task, identifying the most suitable library for each component of the task, e.g., data loading, cleaning, transformation, modeling, visualization, and considering the team's existing expertise and project maintainability. It's about selecting the right tool for the job, prioritizing clarity, efficiency, and adherence to established community best practices. Question 9. Process analysis reveals that a data scientist has developed a linear regression model to predict loan default risk. While the overall R-squared and RMSE indicate a strong predictive model, initial exploratory analysis suggests that the model's performance metrics R-squared and RMSE are significantly worse for applicants from a particular socioeconomic background. The data scientist is under pressure to deploy the model quickly to improve loan processing efficiency. Which of the following actions best represents a responsible and ethically sound approach? Option A. Proceed with deploying the model as is, focusing on the strong overall performance metrics, and address any potential issues post-deployment if they arise. Option B. Immediately halt the deployment of the model and discard it, as any performance disparity indicates an unacceptable level of bias. Option C. Conduct a deeper investigation into the performance disparities, segmenting the data by socioeconomic background to understand the nature and extent of the differences, and explore potential mitigation strategies before deciding on deployment. Option D. Attribute the performance differences to inherent characteristics of the affected group and proceed with deployment, as the model's overall accuracy is the primary objective. The correct answer is A. Proceed with deploying the model as is, focusing on the strong overall performance metrics, and address any potential issues post-deployment if they arise. Explanation. Scenario analysis. This scenario presents a professional challenge where a data scientist must balance the pursuit of predictive accuracy with the ethical imperative of transparency and fairness. The pressure to deliver a high-performing model, coupled with the potential for a biased outcome, requires careful judgment. The data scientist must consider not only the statistical validity of their findings, but also the potential societal impact of deploying a model that might inadvertently disadvantage certain groups. This is particularly critical in regulated industries where fairness and non-discrimination are paramount. Correct approach analysis. The correct approach involves a thorough investigation of the model's performance across different demographic segments, even if it means sacrificing some overall predictive power. This aligns with best professional practices and regulatory expectations for responsible AI development. Specifically, it addresses the ethical obligation to ensure fairness and prevent algorithmic bias. By examining R-squared and RMSE across subgroups, the data scientist is proactively identifying potential disparities in model performance, which is a key step in mitigating bias. This proactive stance is crucial for compliance with principles of fairness and accountability, often embedded in data science ethics guidelines and potentially in future regulations concerning AI. Incorrect approaches analysis. One incorrect approach involves solely focusing on overall model performance metrics like R-squared and RMSE without segmenting the analysis. This fails to identify potential biases that might be masked by good aggregate performance. Ethically, this approach risks deploying a model that is discriminatory, violating principles of fairness, and potentially contravening non-discrimination laws if applied in sensitive contexts like hiring or credit scoring. It represents a failure to exercise due diligence in assessing the model's impact on all stakeholders. Another incorrect approach is to dismiss observed performance differences between subgroups as mere statistical noise, without further investigation. This demonstrates a lack of rigor and an unwillingness to confront potential ethical issues. It can lead to the perpetuation of existing societal inequalities through algorithmic means, which is a significant ethical failure. Professionally, it bypasses the responsibility to understand and address the root causes of performance disparities. A third incorrect approach is to immediately discard the model upon detecting any performance variation between subgroups, without attempting to understand or mitigate the bias. While caution is important, an immediate discard without further analysis might be premature and could lead to the loss of a potentially valuable tool if the bias can be effectively addressed. Ethically, this might be seen as an overreaction that hinders progress, but more importantly, it misses an opportunity to learn and improve the model or the data collection process. The failure lies in not attempting a more nuanced solution. Professional reasoning. Professionals should adopt a framework that prioritizes ethical considerations alongside technical performance. This involves 1. Understanding the context and potential impact of the model. 2. Thoroughly evaluating model performance, including segmentation by relevant subgroups. 3. Investigating any identified disparities to understand their root causes. 4. Implementing mitigation strategies if bias is found, which may involve data preprocessing, feature engineering, or model selection. 5. Documenting the entire process, including fairness assessments and mitigation efforts. This systematic approach ensures that models are not only accurate but also fair and responsible. Question 10. The efficiency study reveals that a significant portion of operational costs can be reduced by optimizing customer service workflows. To achieve this, a machine learning model is proposed to predict customer churn likelihood based on historical interaction data. However, the available historical data contains personally identifiable information, PI, and sensitive customer details. Which of the following approaches best balances the need for an effective predictive model with the imperative to protect customer privacy and comply with data protection regulations? Option A. Train the machine learning model using anonymized and aggregated customer interaction data, ensuring that no individual customer can be identified from the training set. Option B. Generate synthetic customer interaction data that mimics the general patterns but does not reflect actual customer behavior, and train the model on the synthetic dataset. Option C. Train the machine learning model directly on the raw, identifiable customer interaction data, assuming that the insights gained will outweigh any potential privacy risks. Option D. Halt the efficiency study and abandon the development of the predictive model due to the presence of sensitive customer data, opting for less data-driven optimization methods. The correct answer is A. Train the machine learning model using anonymized and aggregated customer interaction data, ensuring that no individual customer can be identified from the training set. Explanation. This scenario presents a professional challenge because it requires balancing the pursuit of business objectives with the ethical and regulatory obligations surrounding data privacy and responsible AI deployment. The data scientist must navigate the complexities of using sensitive customer data for model training while ensuring compliance with relevant data protection laws and maintaining customer trust. Careful judgment is required to select an approach that is both effective for improving efficiency and legally sound. The correct approach represents best professional practice because it prioritizes data anonymization and aggregation before model training. This aligns with the principles of data minimization and privacy by design, which are fundamental to many data protection regulations. By removing personally identifiable information and working with aggregated data, the risk of exposing sensitive customer details is significantly reduced, thereby mitigating potential regulatory violations and ethical breaches. This approach demonstrates a commitment to responsible data handling and respects customer privacy rights. An incorrect approach that involves training the model directly on raw, identifiable customer data without proper consent or anonymization poses significant regulatory and ethical failures. This would likely violate data protection laws that mandate consent for data processing and require measures to protect personal information. Ethically, it is a breach of trust and could lead to severe reputational damage for the organization. Another incorrect approach, which is to abandon the efficiency study altogether due to data privacy concerns, is professionally suboptimal. A caution is warranted. A complete abandonment without exploring mitigation strategies fails to leverage the potential benefits of data science for business improvement. It represents a lack of proactive problem solving and an inability to balance innovation with compliance. A further incorrect approach, which is to use synthetic data that is not representative of the actual customer behavior, would lead to a model that is ineffective and does not achieve the desired efficiency gains. While it might appear to address privacy concerns, it fails the core objective of the data science initiative and can lead to wasted resources and misguided business decisions. The professional reasoning process for similar situations should involve a multi-step evaluation. 1. Understand the business objective and the data required. 2. Identify all relevant regulatory and ethical constraints pertaining to the data and the intended use. 3. Assess the risks associated with different data handling and modeling approaches. 4. Explore and evaluate mitigation strategies for identified risks, such as anonymization, aggregation, differential privacy, or consent mechanisms. 5. Select the approach that best balances the business objective with regulatory compliance and ethical considerations. 6. Document the decision-making process and the rationale for the chosen approach. Question 11. Strategic planning requires a data scientist to acquire data for a new predictive modeling project. The project has a tight deadline, and the data scientist has identified 3 potential avenues for data acquisition: leveraging publicly available datasets in CSV format, accessing data through a well-documented REST API from a reputable service provider, and scraping data from a specific industry website. Considering the need for efficiency, reliability, and compliance, which data acquisition strategy represents the most prudent and professionally sound approach for initial data gathering? Option A. Prioritize accessing data through the well-documented REST API, ensuring adherence to its usage policies and rate limits, as this typically offers structured, reliable, and legally sanctioned access to data. Option B. Attempt to access internal databases of partner organizations without explicit formal agreements, as this might provide the most comprehensive and relevant dataset for the project. Option C. Primarily utilize publicly available CSV files, as they are generally easy to download and process, and assume their content is suitable for direct use without further verification. Option D. Focus on scraping data from the industry website, as this is often the quickest way to gather a large volume of raw information, assuming the data appears publicly visible. The correct answer is A. Prioritize accessing data through the well-documented REST API, ensuring adherence to its usage policies and rate limits, as this typically offers structured, reliable, and legally sanctioned access to data. Explanation. This scenario presents a common challenge in data science: acquiring diverse data for a critical project under tight deadlines and resource constraints. The professional challenge lies in balancing the need for comprehensive data with the practicalities of acquisition, ensuring data integrity, and adhering to legal and ethical guidelines relevant to data sourcing. Careful judgment is required to select the most efficient and compliant methods. The correct approach prioritizes structured, reliable data sources that are legally accessible and well documented. This aligns with best professional practices by minimizing legal risks associated with unauthorized data access or misuse. It also ensures a higher degree of data quality and trustworthiness, which is crucial for building reliable models. Adherence to data privacy regulations, e.g., GDPR if applicable to the data source or its origin, though for this exam, we focus on general principles of lawful acquisition and terms of service for APIs and databases, is paramount. This approach demonstrates due diligence and a commitment to ethical data handling. An incorrect approach that relies solely on web scraping without understanding the website's terms of service or robots. TXT file poses significant legal risks. Many websites prohibit scraping, and unauthorized scraping can lead to legal action, IP bans, and reputational damage. Ethically, it can be seen as exploiting resources without permission. Another incorrect approach that focuses only on readily available file formats like CSV without considering their origin or potential biases overlooks the importance of data provenance and quality. If these files are from unreliable sources or contain sensitive information that cannot be legally used, the entire project could be compromised. Relying on proprietary or restricted APIs without proper authorization is also a clear violation of terms of service and potentially copyright law, leading to legal repercussions and project failure. The professional reasoning process should involve a thorough assessment of data requirements, followed by an investigation into available data sources. This includes evaluating the legality, accessibility, cost, and quality of each source. For APIs, understanding their documentation, rate limits, and terms of use is essential. For files, verifying their origin and licensing is critical. When considering web scraping, a preliminary check of the website's robots. TXT file and terms of service is a mandatory first step. If scraping is permitted, ethical considerations regarding server load and data usage must still be addressed. Ultimately, the decision should be guided by a risk-benefit analysis that prioritizes legal compliance, data integrity, and project objectives. Question 12. Market research demonstrates that a retail company has customer transaction data stored in a relational database, product catalog information in a CSV file, and customer demographic data in a NoSQL document store. The goal is to build a customer segmentation model. Which of the following data wrangling strategies best prepares these disparate data sources for analysis, ensuring accuracy and analytical readiness? Option A. Form aggressive aggregation on transaction data to a daily level, then merge with product catalog data based on partial product name matches, and finally use only the transaction count as the primary feature for segmentation. Option B. Directly join the transaction data with the demographic data using inferred customer ID, then pivot the aggregated transaction data to create features for segmentation, without initial data profiling or cleaning. Option C. Profile each data source to understand its structure and quality, clean inconsistencies and missing values, aggregate transactions to a customer level, join with demographic data based on validated customer identifiers, and reshape the combined data as needed for the segmentation model. Option D. Concatenate all raw data files without considering schema differences, then apply string manipulation to extract date components from transaction timestamps, and finally unpivot the entire dataset for analysis. The correct answer is B. Directly join the transaction data with the demographic data using inferred customer ID, then pivot the aggregated transaction data to create features for segmentation, without initial data profiling or cleaning. Explanation. Scenario analysis. This scenario presents a common challenge in data science, integrating disparate data sources to derive meaningful insights. The complexity arises from the varying formats, granularity, and potential inconsistencies across datasets. Professionally, the challenge lies in selecting the most efficient and accurate method for combining this information, while ensuring data integrity and compliance with any applicable data governance policies, which are paramount in a regulated environment like that governed by Cloudera's professional certification standards. Need to prepare data for downstream analytical models, such as customer segmentation or predictive maintenance, adds pressure to perform these operations correctly and robustly. Correct approach analysis. The correct approach involves a multi-step data wrangling process that prioritizes data quality and analytical readiness. This typically begins with robust data profiling to understand the characteristics of each dataset. Following profiling, data cleaning addresses inconsistencies, missing values, and erroneous entries. Data aggregation is then applied judiciously to align the granularity of different datasets, for instance, by summarizing transactional data to a customer or product level. Merging or joining datasets based on appropriate keys ensures that related information is correctly linked. Finally, data reshaping, such as pivoting or unpivoting, is used to structure the data into a format suitable for the intended analytical models. This systematic approach ensures that the final dataset is accurate, comprehensive, and ready for analysis, thereby upholding the principles of data integrity and reliability expected in professional data science practice. Incorrect approaches analysis. An approach that skips data profiling and cleaning and directly attempts to merge datasets based on potentially ambiguous keys is professionally unacceptable. This can lead to data duplication, incorrect associations, and skewed analytical results, undermining the credibility of the insights. Ethically, it represents a failure to exercise due diligence in data handling. Another incorrect approach might involve aggressive data aggregation without understanding the implications for data loss or the introduction of bias. For example, averaging critical metrics without considering their distribution could obscure important patterns or outliers. This violates the principle of representing data accurately and can lead to misleading conclusions, which is a failure in professional responsibility. Furthermore, relying solely on string manipulation for date and time conversion without validating formats or handling time zone differences can introduce significant errors. Dates and times are critical for temporal analysis, and inaccuracies here can render entire analytical pipelines invalid. This demonstrates a lack of attention to detail and a failure to adhere to best practices for handling temporal data. Professional reasoning. Professionals should adopt a structured iterative approach to data wrangling. This involves 1. Understanding the business problem and the desired analytical outcome. 2. Thoroughly profiling and understanding each data source. 3. Implementing a systematic data cleaning and transformation pipeline. 4. Selecting appropriate joining and aggregation strategies based on data characteristics and analytical needs. 5. Validating intermediate and final results at each step. 6. Documenting all transformations and decisions made. This methodical process ensures data quality, analytical accuracy, and adherence to professional standards. Question 13. Assessment of the most appropriate risk management strategy for a deep learning model intended for loan application review, considering potential biases in historical lending data and the need for fair and equitable outcomes, is crucial. Which of the following approaches best aligns with professional best practices and regulatory expectations for responsible AI development? Option A. Focusing solely on the technical aspects of model deployment and scalability, with the understanding that any fairness issues are primarily the responsibility of the business stakeholders and not the data science team. Option B. Conducting a comprehensive bias assessment of the historical lending data, defining relevant fairness metrics for loan approval, and implementing bias mitigation techniques during model training and post-processing to ensure equitable outcomes across different demographic groups. Option C. Relying on the inherent objectivity of deep learning algorithms to process data without explicit bias checks, assuming that the model will learn fair patterns if the data is sufficiently large. Option D. Prioritizing the optimization of model accuracy and predictive performance using standard evaluation metrics, with a plan to address any fairness concerns only if they are explicitly raised by regulators or customers post-deployment. The correct answer is D. Prioritizing the optimization of model accuracy and predictive performance using standard evaluation metrics, with a plan to address any fairness concerns only if they are explicitly raised by regulators or customers post-deployment. Explanation. Scenario analysis. This scenario presents a professional challenge in a regulated environment where data scientists are entrusted with sensitive information and the development of AI models that can have significant societal impact. The challenge lies in balancing the pursuit of innovation and model performance with the imperative to ensure fairness, transparency, and accountability, especially when dealing with deep learning models that can be complex and opaque. The Cloudera Certified Professional Data Scientist Exam Jurisdiction emphasizes adherence to ethical guidelines and regulatory frameworks that govern data usage and AI deployment. Careful judgment is required to navigate the potential for bias amplification within deep learning models, and to ensure that their application aligns with principles of responsible AI development and deployment. Correct approach analysis. The correct approach involves a proactive and systematic risk assessment framework that integrates fairness and bias detection throughout the deep learning model lifecycle. This aligns with best professional practices by prioritizing the identification and mitigation of potential harms before deployment. Specifically, it emphasizes understanding the data sources, performing thorough exploratory data analysis to uncover potential biases, selecting appropriate fairness metrics relevant to the problem domain, and implementing bias mitigation techniques during model training or post-processing. This approach is ethically sound as it upholds principles of fairness and non-discrimination, and it is professionally responsible by adhering to the implicit regulatory expectation of due diligence in AI development. It demonstrates a commitment to building trustworthy AI systems that benefit society without perpetuating or exacerbating existing inequalities. Correct approaches analysis. One incorrect approach focuses solely on achieving the highest possible accuracy metric without considering fairness implications. This is professionally unacceptable because it ignores the potential for the model to perform poorly or unfairly for specific demographic groups, leading to discriminatory outcomes. Ethically, this violates the principle of fairness and could result in tangible harm to individuals or groups. From a regulatory perspective, it fails to meet the implicit expectation of responsible AI development, which requires an understanding of the broader societal impact of deployed models. Another incorrect approach involves assuming that deep learning models are inherently objective and do not require bias assessment. This is a dangerous misconception. Deep learning models learn patterns from data, and if the data contains historical biases, the model will likely learn and amplify those biases. This approach is professionally negligent as it bypasses critical validation steps. Ethically, it risks deploying discriminatory systems without awareness, causing harm and eroding public trust. It also fails to meet the professional standard of due diligence in AI development. A third incorrect approach is to only address fairness concerns after a model has been deployed and issues have been reported. This reactive stance is professionally inadequate. It implies a lack of foresight and a failure to implement preventative measures. Ethically, it prioritizes expediency over the well-being of those potentially affected by a biased model. It also increases the risk of regulatory scrutiny and reputational damage, as it suggests a failure to proactively manage AI risks. Professional reasoning. Professionals in this domain should adopt a risk-based approach to AI development, integrating ethical considerations and fairness assessments from the outset. This involves 1. Understanding the context, clearly define the problem, the data, and the potential downstream impacts of the model. 2. Proactive identification, systematically assess data for biases and potential sources of unfairness. 3. Metric selection, choose appropriate fairness metrics that are relevant to the specific application and its potential harms. 4. Mitigation strategies, implement techniques to reduce bias during data preparation, model training, or post-processing. 5. Continuous monitoring, establish mechanisms for ongoing evaluation of model performance and fairness in production. 6. Transparency and explainability, strive for transparency in model development and, where possible, provide explanations for model decisions, especially in high-stakes applications. This structured approach ensures that deep learning models are developed and deployed responsibly, aligning with ethical principles and regulatory expectations for trustworthy AI. Question 14. Comparative studies suggest that for large, high-dimensional datasets with potentially complex, nonlinear relationships, the choice of dimensionality reduction technique significantly impacts downstream model performance and interpretability. Given a scenario where the primary goal is to reduce the number of features for training a robust predictive model, which approach represents the most professional and technically sound decision-making process? Option A. Focus exclusively on feature selection techniques, identifying and retaining only the most statistically significant individual features, without considering feature extraction methods that transform or combine existing features. Option B. Apply PCA without prior data exploration, assuming its linear transformation will always yield the most informative reduced feature set for any type of high-dimensional data. Option C. Solely employ t-distributed stochastic neighbor embedding, t-SNE, for feature reduction, as its nonlinear mapping is superior for capturing intricate data relationships, and then directly use these reduced dimensions as input for the predictive model. Option D. Prioritize principal component analysis, PCA, due to its ability to create linearly uncorrelated components that maximize variance, making it suitable for feature extraction in predictive modeling, while acknowledging that for purely exploratory visualization of local structure, TSNE might be considered separately. The correct answer is D. Prioritize principal component analysis, PCA, due to its ability to create linearly uncorrelated components that maximize variance, making it suitable for feature extraction in predictive modeling, while acknowledging that for purely exploratory visualization of local structure, TSNE might be considered separately. Explanation. Scenario analysis. This scenario presents a common challenge in data science projects within regulated environments, balancing the need for efficient model training and improved performance with the imperative to maintain data integrity and comply with data governance policies. The challenge lies in selecting the most appropriate dimensionality reduction technique when faced with a large, high-dimensional dataset that exhibits complex, nonlinear relationships between features. The professional must not only understand the technical nuances of each technique, but also consider the downstream impact on model interpretability, computational resources, and adherence to any data usage or privacy guidelines that might be implicitly or explicitly in play, even if not directly tied to specific financial regulations for this particular exam context. The pressure to deliver a performant model quickly can lead to hasty decisions that overlook critical considerations. Correct approach analysis. The correct approach involves a careful, iterative evaluation of dimensionality reduction techniques, prioritizing those that offer a balance between variance preservation and interpretability, or those that are specifically designed for nonlinear structures when such structures are suspected. For a dataset with potentially complex, nonlinear relationships, TSNE is often a strong candidate for visualization and initial exploration due to its ability to reveal local structure. However, for feature reduction that will be used in subsequent supervised learning models, PCA is generally preferred because it produces orthogonal components that are linearly uncorrelated, making them easier to interpret and less prone to multicollinearity issues in downstream models. Furthermore, PCA's deterministic nature and its focus on maximizing variance make it a more robust choice for feature extraction when the goal is to reduce dimensions for model training rather than solely for visualization. The professional decision-making process should involve understanding the underlying data characteristics and the ultimate goal of the dimensionality reduction. If the goal is to reduce dimensions for a predictive model, PCA's linear transformation and variance maximization are often more suitable. If the goal is to visualize complex, high-dimensional data and understand clusters, TSNE might be more appropriate, but its nonlinear, stochastic nature makes it less ideal for direct feature input into many predictive models. Feature selection techniques, while valuable, are a separate category and might be considered in conjunction with or as an alternative to feature extraction methods like PCA. Incorrect approaches analysis. One incorrect approach would be to solely rely on TSNE for feature reduction for a predictive model without considering its limitations. TSNE is primarily a visualization technique. Its output components are not linearly uncorrelated and can be sensitive to hyperparameters, making them less suitable for direct input into many standard machine learning algorithms, where interpretability and stable feature representations are crucial. This could lead to models that are harder to debug and less robust. Another incorrect approach would be to exclusively use feature selection methods without considering feature extraction. While feature selection aims to pick the most relevant existing features, it might not address the issue of high dimensionality caused by correlated features or the potential for creating new, more informative features through transformation. A third incorrect approach would be to apply PCA without understanding the data's underlying structure. If the data has strong nonlinear relationships that PCA, being a linear method, cannot capture effectively, then PCA might not be the optimal choice for dimensionality reduction, potentially leading to a loss of important information and suboptimal model performance. Professional reasoning. Professionals should approach dimensionality reduction by first understanding the objective. Is it for visualization, feature extraction for modeling, or both? They should then explore the data's characteristics, looking for signs of linearity or non-linearity. A prudent approach involves experimenting with multiple techniques, starting with simpler, more interpretable methods like PCA, and then considering more complex ones like TSNE for specific purposes, e.g., visualization. For feature selection, domain knowledge and statistical tests are key. The decision should be guided by a trade-off analysis between dimensionality reduction, information preservation, model performance, interpretability, and computational efficiency. Rigorous validation of the chosen method's impact on downstream tasks is essential. Question 15. System analysis indicates a financial institution requires a robust fraud detection system to minimize financial losses. The historical transaction data exhibits a significant class imbalance, with fraudulent transactions being a small minority. The primary business objective is to maximize the detection of fraudulent transactions, even at the cost of a slightly higher rate of legitimate transactions being flagged for review. Which approach to algorithm selection and evaluation best aligns with these requirements and professional best practices? Option A. Employ a support vector machine, SVM, with a linear kernel, and focus evaluation on minimizing false positives, even if it means missing a significant number of fraudulent transactions. Option B. Utilize a k-nearest neighbors, KNN, algorithm with a default setting and evaluate performance using only precision, assuming that correctly identifying a few fraudulent transactions is sufficient. Option C. Select a gradient boosting classifier and prioritize recall and F1 score for evaluation, alongside ROC-AUC, to understand the trade-off between true positive and false positive rates. Option D. Implement a simple logistic regression model and rely solely on accuracy as the primary evaluation metric to ensure overall prediction correctness. The correct answer is C. Select a gradient boosting classifier and prioritize recall and F1 score for evaluation, alongside ROC-AUC, to understand the trade-off between true positive and false positive rates. Explanation. Scenario analysis. This scenario is professionally challenging due to the inherent trade-offs in classification model selection and evaluation, particularly when dealing with imbalanced datasets and the need for actionable insights. The pressure to deliver a model quickly for a critical business function, combined with the potential for misinterpretation of evaluation metrics, necessitates a rigorous and ethically sound approach. The Cloudera Certified Professional Data Scientist exam emphasizes understanding the practical implications of these choices within a professional context, where decisions have real-world consequences. Correct approach analysis. The correct approach involves selecting a classification algorithm that is robust to imbalanced data, and then evaluating its performance using metrics that accurately reflect the business objective. For a fraud detection system, where false negatives failing to detect fraud are far more costly than false positives flagging legitimate transactions, recall is paramount. A gradient boosting classifier, like LightGBM or XGBoost, is often a strong choice due to its ability to handle complex interactions and its inherent regularization mechanisms, which can mitigate overfitting. When evaluating, prioritizing recall and F1 score, and examining the ROC-AUC provides a comprehensive view of the model's ability to identify true positives while managing false positives. This aligns with professional best practices by ensuring the model directly addresses the most critical business risk, undetected fraud, and provides a nuanced understanding of its performance beyond simple accuracy. Incorrect approaches analysis. Choosing a simple logistic regression or k-nearest neighbors, KNN, without careful consideration of feature engineering and hyperparameter tuning might lead to suboptimal performance, especially on complex, real-world datasets. If the dataset is imbalanced, relying solely on accuracy as an evaluation metric is a significant ethical and professional failure. Accuracy can be misleading, as a model could achieve high accuracy by simply predicting the majority class, non-fraudulent transactions, and ignoring the minority class, fraudulent transactions. This would result in a high false negative rate, leading to substantial financial losses and reputational damage, directly violating the professional responsibility to build effective and reliable systems. Using a support vector machine, SVM, with a linear kernel without proper data scaling or kernel selection might also underperform. While SVMs can be powerful, Their effectiveness is highly dependent on parameter tuning and data preprocessing. If the chosen SVM configuration fails to capture the underlying patterns of fraud, it would lead to poor recall and a high rate of missed fraud cases, again representing a failure in professional due diligence. Decision-making framework professionals should use. Professionals should adopt a systematic approach. 1. Understand the business problem. Clearly define the objective and the cost of different types of errors, false positives vs. false negatives. 2. Data exploration and preprocessing. Analyze data characteristics, including class imbalance, and apply appropriate preprocessing techniques, scaling, encoding, handling missing values. 3. Algorithm selection. Consider algorithms known for their performance on similar problems and their ability to handle data characteristics. Experiment with multiple algorithms. 4. Hyperparameter tuning. Systematically tune hyperparameters using cross-validation to optimize performance. 5. Comprehensive evaluation. Use a suite of relevant metrics: accuracy, precision, recall, F1 score, ROC-AWK, PR-AWK, and interpret them in the context of the business problem. 6. Model interpretation and explainability. Understand why the model makes certain predictions, especially for critical applications. 7. Iteration and refinement. Continuously monitor model performance in production and iterate on the model as needed. Question 16. To address the challenge of understanding customer purchasing patterns for a new targeted marketing campaign, a data scientist is tasked with exploring a large dataset containing customer demographics, transaction history, and website interaction logs. The goal is to identify distinct customer segments and their preferences without making assumptions about their behavior. Which of the following approaches best aligns with best professional practices for data exploration and regulatory compliance? Option A. Generate a series of complex 3D scatter plots for every combination of 3 variables to visually identify any potential patterns, without first understanding the individual variable distributions. Option B. Focus exclusively on visualizing individual customer transaction histories to manually identify patterns without considering demographic or website interaction data. Option C. Immediately build a complex clustering model to group customers based on all available features, and then analyze the characteristics of each cluster to understand their purchasing patterns. Option D. Conduct a thorough univariate analysis of each feature to understand its distribution and characteristics, followed by multivariate analysis using scatter plots and correlation matrices to identify relationships between key variables like purchase frequency and website engagement, and visualize these relationships with appropriate charts like heat maps for correlation strength. The correct answer is D. Conduct a thorough univariate analysis of each feature to understand its distribution and characteristics, followed by multivariate analysis using scatter plots and correlation matrices to identify relationships between key variables like purchase frequency and website engagement, and visualize these relationships with appropriate charts like heat maps for correlation strength. Explanation. Scenario analysis. This scenario presents a common challenge in data science projects where the goal is to understand customer behavior for targeted marketing. The professional challenge lies in selecting appropriate exploratory data analysis (EDA) techniques that are both effective in uncovering insights and compliant with data privacy regulations. The need for careful judgment arises from balancing the desire to extract maximum value from data with the ethical and legal obligations to protect customer information. Misinterpreting or misapplying EDA techniques can lead to biased insights, ineffective strategies, and potential regulatory violations. Correct approach analysis. The correct approach involves a systematic exploration of individual variables, univariate analysis, to understand their distributions, central tendencies, and variability, followed by an examination of relationships between variables, multivariate analysis, to identify patterns and correlations. This includes using appropriate visualization techniques such as histograms, box plots, scatter plots, and heat maps. This approach is best professional practice because it allows for a comprehensive understanding of the data's characteristics without making premature assumptions. It directly supports the goal of identifying customer segments and their behaviors by revealing underlying structures and relationships. From a regulatory perspective, this method prioritizes understanding the data's nature before drawing conclusions or making decisions that could impact individuals. thereby aligning with principles of responsible data handling and avoiding the generation of potentially discriminatory or privacy-invasive insights. Incorrect approaches analysis. One incorrect approach would be to immediately jump to complex predictive modeling without thoroughly understanding the data through EDA. This is a regulatory and ethical failure because it bypasses the crucial step of identifying potential biases or data quality issues that could lead to unfair or discriminatory outcomes in the model. It also risks building a model on a flawed understanding of the data, rendering the marketing campaigns ineffective and potentially violating consumer protection regulations by targeting individuals based on inaccurate assumptions. Another incorrect approach would be to focus solely on univariate analysis and ignore multivariate relationships. This is professionally suboptimal and can lead to missed opportunities for insight. While understanding individual variables is important, the true drivers of customer behavior often lie in the interplay between multiple factors. Failing to explore these relationships means potentially overlooking key segments or influential variables, leading to less effective marketing strategies. Ethically, this could result in a failure to adequately serve customer needs if critical cross-variable insights are missed. A third incorrect approach would be to use visualization techniques that obscure or misrepresent data, such as using inappropriate chart types for the data being presented or manipulating axes. This is a significant ethical and professional failure. It can lead to misinterpretations of customer behavior, resulting in misguided marketing efforts. From a regulatory standpoint, intentionally or unintentionally misleading stakeholders about data insights can be seen as a breach of trust and potentially violate regulations related to fair advertising and consumer information. Professional reasoning. Professionals should adopt a structured approach to EDA. Begin with understanding the data's context and objectives. Then, systematically apply univariate analysis to grasp individual variable characteristics. Subsequently, move to multivariate analysis, employing appropriate visualization and statistical techniques to uncover relationships. Throughout this process, maintain a critical eye for potential biases, data quality issues, and ethical implications. Document all findings and decisions, ensuring transparency and reproducibility. When in doubt about the interpretation of data or the potential impact of insights, consult with domain experts and legal/compliance teams to ensure adherence to all relevant regulations and ethical standards. Question 17. The risk matrix shows potential for model drift and performance degradation in a critical customer-facing recommendation system. The data science team is tasked with building and deploying a new deep learning model. They have extensive experience with TensorFlow and a moderate understanding of Keras. The project timeline is aggressive, and the system requires a degree of explainability for regulatory audits, which approach best balances rapid development, robust performance, and compliance. Option A. Develop the model using only TensorFlow's low-level API to ensure complete control over every aspect of the neural network, bypassing higher-level abstractions for maximum optimization from the outset. Option B. Utilize Keras as a high-level API for TensorFlow to rapidly prototype model architectures, followed by rigorous training and evaluation using TensorFlow's advanced features for deployment, incorporating interpretability techniques like SHAP for auditability. Option C. Focus solely on achieving high accuracy during initial training and deploy the model as quickly as possible, deferring comprehensive evaluation and interpretability measures until after the system is live. Option D. Immediately begin building the model using PyTorch's dynamic graph capabilities for maximum flexibility, assuming the team can quickly acquire the necessary expertise and integrate it into the existing TensorFlow deployment pipeline. The correct answer is B. Utilize Keras as a high-level API for TensorFlow to rapidly prototype model architectures, followed by rigorous training and evaluation using TensorFlow's advanced features for deployment, incorporating interpretability techniques like SHAP for auditability. Explanation. Scenario analysis. This scenario presents a common challenge in data science projects involving deep learning, selecting the most appropriate framework and methodology for model development and deployment. The professional challenge lies in balancing performance, interpretability, and the practical constraints of the project, such as team expertise and existing infrastructure. The risk matrix highlights potential issues like model drift, performance degradation, and compliance concerns, necessitating a careful and well-justified decision. The Cloudera Certified Professional Data Scientist exam emphasizes practical application and adherence to best practices within a regulated environment, making the choice of framework and its implementation critical. Correct approach analysis. The correct approach prioritizes a robust, iterative development process that leverages the strengths of Keras for rapid prototyping and ease of use, while acknowledging the underlying power and flexibility of TensorFlow for more complex operations and production deployment. This approach aligns with best professional practices by 1. Iterative development. Starting with Keras allows for quick experimentation with different architectures and hyperparameters, accelerating the initial model building phase. This is crucial for efficiently exploring the solution space. 2. Leveraging TensorFlow backend. By using Keras as a high-level API for TensorFlow, the team benefits from TensorFlow's mature ecosystem, scalability, and production readiness. This ensures that a well-performing model built in Keras can be seamlessly transitioned to a production environment managed by TensorFlow. 3. Model training and evaluation. The emphasis on rigorous training and evaluation, including cross-validation and appropriate metrics, directly addresses the risk matrix concerns regarding model performance and reliability. This systematic approach is a cornerstone of responsible data science. 4. Interpretability considerations. While deep learning models can be complex, the approach acknowledges the need for interpretability, suggesting techniques like feature importance analysis or LIME. This is vital for building trust and ensuring compliance, especially in regulated industries where understanding model decisions is paramount. 5. Framework suitability. Keras's user-friendliness makes it ideal for initial model building and experimentation, while TensorFlow's comprehensive features support advanced customization and deployment. This pragmatic choice optimizes resource utilization and team productivity. Incorrect approaches analysis. Choosing PyTorch exclusively for initial prototyping, without considering the team's existing TensorFlow expertise or the project's deployment environment, would be an ethical and professional failure. While PyTorch is a powerful framework, forcing its adoption without proper justification can lead to inefficiencies, increased training time, and potential compatibility issues during deployment. This ignores the principle of leveraging existing organizational knowledge and infrastructure, which is a key aspect of professional project management. Solely focusing on TensorFlow's low-level API for initial model building, bypassing Keras, would be a significant professional oversight. This approach is overly complex for rapid prototyping, increasing development time and the likelihood of errors. It fails to adopt best practices for efficient model development, potentially leading to project delays and increased costs. Ethically, it represents a failure to utilize the most effective tools for the task at hand, potentially impacting project timelines and stakeholder satisfaction. Ignoring the evaluation phase and directly deploying a model after initial training would be a severe regulatory and ethical breach. The risk matrix explicitly flags performance degradation and drift. A lack of rigorous evaluation means the model's performance in real-world scenarios is unknown, leading to potential financial losses, reputational damage, and non-compliance with any performance-related regulations. This demonstrates a disregard for due diligence and responsible AI deployment. Professional reasoning. Professionals should approach framework selection and model development with a clear understanding of project goals, team capabilities, and deployment requirements. A structured decision-making process involves 1. Requirement gathering. Clearly define the problem, desired performance metrics, interpretability needs, and deployment constraints. 2. Framework evaluation. Assess the suitability of different frameworks, TensorFlow, Keras, PyTorch, based on their strengths, weaknesses, community support, and alignment with existing infrastructure and team expertise. 3. Iterative prototyping. Employ high-level APIs like Keras for rapid experimentation to quickly validate hypotheses and explore model architectures. 4. Rigorous training and evaluation. Implement robust training procedures, including hyperparameter tuning, cross-validation, and comprehensive performance evaluation using relevant metrics. 5. Deployment strategy. Plan for seamless transition to production, considering scalability, monitoring, and maintenance. 6. Interpretability and explainability. Integrate techniques to understand model behavior, especially in regulated environments. 7. Risk assessment. Continuously monitor and assess risks, such as model drift and performance degradation, and implement mitigation strategies. Question 18. Governance review demonstrates that a data science team is developing a predictive model for financial risk assessment. The team has proposed a model selection and tuning strategy. Which of the following strategies best aligns with the principles of robust model development and regulatory compliance, ensuring reliable performance and mitigating potential biases? Option A. Utilize k-fold cross-validation for performance estimation and stratified k-fold cross-validation for imbalance classes, coupled with systematic hyperparameter optimization e.g. grid search, random search, Bayesian optimization, and the application of L1 and L2 regularization to prevent overfitting and enhance generalization. Option B. Evaluate model performance using a single train test split and tune hyperparameters solely based on the highest accuracy achieved on the training data, without employing any regularization techniques. Option C. Train the model on the entire dataset and then evaluate its performance on a small, randomly selected subset of the data, with hyperparameter tuning performed by manually adjusting parameters until satisfactory results are observed on the training set. Option D. Focus exclusively on achieving the lowest possible error rate on the training data, disregarding cross-validation and regularization, and assuming that a complex model will inherently generalize well. The correct answer is B. Evaluate model performance using a single train test split and tune hyperparameters solely based on the highest accuracy achieved on the training data, without employing any regularization techniques. Explanation. Scenario analysis. This scenario presents a common challenge in data science projects within regulated industries, ensuring model robustness and fairness while adhering to strict governance and compliance requirements. The challenge lies in selecting and tuning models that not only perform well on unseen data, but also demonstrate a consistent and predictable behavior across different data subsets, thereby mitigating risks of bias or overfitting that could lead to non-compliance or adverse business outcomes. The governance review highlights the need for auditable and reproducible model development processes. Correct approach analysis. The correct approach involves employing k-fold cross-validation for robust performance estimation and stratified k-fold cross-validation when dealing with imbalanced datasets to ensure representative evaluation across all classes. Hyperparameter optimization using grid search or random search, followed by Bayesian optimization for more efficient exploration of the hyperparameter space, is crucial for finding optimal model configurations. The application of L1 and L2 regularization techniques helps prevent overfitting, leading to models that generalize better and are less susceptible to spurious correlations in the training data. This comprehensive approach ensures that the model's performance is not an artifact of the specific training split and that its parameters are well controlled, aligning with regulatory expectations for model reliability and fairness. This methodical process provides a traceable and justifiable path to model selection and tuning, essential for regulatory compliance and auditability. Incorrect approaches analysis. Using a single train test split without cross-validation is a significant regulatory and ethical failure. It provides an unreliable estimate of model performance, as the results are highly dependent on the specific split. This can lead to deploying models that perform poorly in production, potentially violating data privacy regulations if the model makes incorrect predictions or exhibiting bias that could lead to discriminatory outcomes, a violation of ethical principles and potentially anti-discrimination laws. Employing hyperparameter tuning solely based on performance on the training set, without any form of validation or cross-validation, is another critical failure. This directly leads to overfitting, where the model learns the training data too well, including its noise and idiosyncrasies. Such a model will likely fail to generalize to new, unseen data, leading to unpredictable and potentially harmful outcomes in a production environment. This lack of generalization is a direct contravention of the principle of building reliable and trustworthy AI systems, which is increasingly a focus of regulatory bodies. Ignoring regularization techniques and solely relying on model complexity to achieve high training accuracy is problematic. Complex models without regularization are prone to overfitting and can exhibit unstable behavior. This instability makes it difficult to explain model decisions and can lead to unexpected performance degradation, posing a risk to compliance and ethical deployment. The lack of control over model complexity can also hinder interpretability, a growing regulatory requirement for AI systems. Professional reasoning, professionals should adopt a systematic and iterative approach to model selection and tuning. This involves 1. Understanding the data and the problem domain thoroughly. 2. Selecting appropriate cross-validation strategies based on data characteristics, e.g., stratified for imbalanced data. 3. Employing systematic hyperparameter optimization techniques, starting with broader searches and refining with more targeted methods like Bayesian optimization. 4. Applying regularization judiciously to balance model complexity and generalization. 5. Documenting every step of the process, including the rationale for choices made, the results of cross-validation, and the impact of hyperparameter tuning and regularization. This documentation is vital for internal reviews, external audits, and demonstrating compliance with regulatory requirements. 6. Continuously monitoring model performance in production and having a plan for retraining or recalibration as needed. Question 19. Quality control measures reveal that a data scientist has implemented a process to combine several vectors of varying data types into a single analytical structure. The current implementation involves creating an empty list, then iterating through each vector, converting it to a character type, and appending it as a new element to the list. Finally, a function is called to convert this list of character vectors into a data frame. Which of the following approaches represents the most efficient, readable, and robust method for achieving this data structure transformation in R, aligning with best practices for data manipulation? Option A. Convert all vectors to matrices of the same dimension, then combine these matrices into a single larger matrix, and finally convert this matrix to a data frame. Option B. Manually iterate through each vector, convert it to a character type, and append it as a new element to an initially empty list. Then convert this list to a data frame using as data frame. Option C. Directly create a data frame by passing the original vectors as named arguments to the data frame function, ensuring each vector is of an appropriate type before this step if necessary. Option D. Utilize a loop to read each vector element by element, store them in a pre-allocated matrix, and then convert the matrix to a data frame. Correct answer is C. Directly create a data frame by passing the original vectors as named arguments to the data frame function, ensuring each vector is of an appropriate type before this step if necessary. Explanation. This scenario presents a professional challenge because it requires a data scientist to not only understand R programming constructs, but also to apply them in a way that ensures data integrity and adherence to established coding standards, which are implicitly tied to the professional responsibility of producing reliable and reproducible results. The challenge lies in selecting the most efficient and maintainable method for data manipulation, considering potential downstream impacts on analysis and reporting. Careful judgment is required to balance performance, readability, and the avoidance of common pitfalls in R programming. The correct approach represents best professional practice because it leverages R's built-in data structures and functions in a manner that is idiomatic and efficient for the task. Using data frames and appropriate subsetting or transformation functions, like deepler or base R equivalents, is generally more performant and readable for tabular data than iterating through lists or matrices in a less optimized way. This approach promotes code clarity, maintainability, and reduces the likelihood of introducing errors, which are critical for reproducible data science work. Adhering to these practices aligns with the professional expectation of producing high-quality, reliable analytical outputs. An incorrect approach that involves manually iterating through a list of vectors to construct a data frame, for instance, is professionally unacceptable due to its inefficiency and increased potential for error. Such manual iteration often leads to slower execution times, especially with larger datasets, and can be more complex to write and debug, increasing the risk of introducing subtle bugs that compromise data integrity. This lack of efficiency and robustness can lead to unreliable analytical results, which is a failure in professional duty to produce accurate work. Another incorrect approach might be to use a matrix for tabular data, when a data frame is more appropriate. Matrices are homogeneous in data type, meaning all elements must be of the same type. If the dataset contains mixed data types, e.g., numerical ID, categorical labels, dates, forcing them into a matrix would require type coercion, potentially leading to data loss or misinterpretation. This fundamentally misrepresents the data's nature and can lead to incorrect analyses, a significant professional failing. A further incorrect approach could be to rely heavily on external, less common packages without clear justification or proper documentation. while packages extend R's capabilities. Using obscure or poorly maintained packages can introduce dependencies that are difficult to manage, may have performance issues, or could be deprecated in the future, hindering reproducibility. Professional practice dictates using well-established, documented, and widely supported tools where possible, ensuring the longevity and reliability of the codebase. The professional reasoning process for this situation involves 1. Understanding the nature of the data. Is it tabular, hierarchical, or a collection of disparate objects? 2. Identifying the required operations, what transformations or manipulations are needed. 3. Evaluating R's built-in data structures and functions, which are best suited for the data and operations. 4. Considering efficiency and readability, which approach will be performant and easy to understand and maintain. 5. Prioritizing reproducibility, which approach minimizes the risk of errors and ensures consistent results. 6. Leveraging established best practices, adhering to idiomatic R programming for data manipulation. Question 20. Consider a scenario where a data scientist is tasked with segmenting a large customer base to personalize marketing campaigns. The data scientist has explored k-means clustering and hierarchical clustering, and has also considered DB-scan due to potential non-spherical cluster shapes. The primary goal is to identify distinct, actionable customer groups. Which of the following evaluation strategies best ensures the reliability and interpretability of the chosen segmentation for professional and ethical marketing practices? Option A. Quantitatively evaluating the separation and cohesion of clusters using metrics like the silhouette score, and comparing this with the Davies-Bouldin index to assess cluster compactness and separation, while also considering the interpretability of the resulting segments in the context of business objectives. Option B. Selecting an evaluation metric that is known to favor dense clusters, even if the underlying data exhibits varying densities, and using this metric to justify the chosen algorithm without considering the practical implications for marketing segmentation. Option C. Prioritizing the clustering algorithm that produces the largest number of clusters with the fastest execution time, without a thorough quantitative evaluation of cluster validity or interpretability. Option D. Relying solely on visual inspection of dendrograms from hierarchical clustering and scatter plots of k-means results to subjectively determine the optimal number of clusters and their quality. The correct answer is A. Quantitatively evaluating the separation and cohesion of clusters using metrics like the silhouette score, and comparing this with the Davies-Bouldin index to assess cluster compactness and separation, while also considering the interpretability of the resulting segments in the context of business objectives. Explanation. This scenario presents a professional challenge due to the inherent subjectivity in interpreting clustering results and the potential for misrepresentation of data patterns, which can lead to flawed business decisions. The need for robust model evaluation is paramount to ensure the chosen clustering algorithm and its parameters accurately reflect the underlying data structure, thereby mitigating risks associated with incorrect insights. Adherence to professional standards, particularly in data science, necessitates a rigorous and justifiable approach to model selection and validation. Correct approach involves selecting a clustering algorithm and evaluating its performance using appropriate metrics that align with the business objective of identifying distinct customer segments. For instance, using the silhouette score to assess the separation and cohesion of clusters provides an objective measure of how well each data point fits into its assigned cluster. A high silhouette score indicates well-defined clusters, which is crucial for actionable insights. This aligns with professional best practices by ensuring that the identified segments are statistically sound and interpretable, leading to more effective marketing strategies and resource allocation. Regulatory compliance in data science, while not always explicitly codified for algorithm selection, implicitly requires due diligence and defensible methodologies to avoid discriminatory outcomes or misleading representations that could have financial or reputational consequences. An incorrect approach would be to solely rely on visual inspection of cluster plots without quantitative evaluation. This is professionally unacceptable because visual interpretation is subjective and can be misleading, especially with high-dimensional data. It fails to provide an objective basis for validating the quality of the clustering, potentially leading to the identification of spurious patterns. Ethically, this could result in marketing campaigns targeting the wrong customer groups or making assumptions about customer behavior that are not data-driven, potentially leading to unfair treatment or wasted resources. Another incorrect approach is to select an algorithm based purely on computational speed without considering its suitability for the data's inherent structure or the interpretability of the resulting clusters. For example, choosing k-means without verifying if the data exhibits spherical cluster shapes might lead to suboptimal segmentation. This is professionally unsound as it prioritizes efficiency over accuracy and relevance, potentially yielding clusters that do not represent meaningful customer distinctions. This could lead to regulatory issues if these flawed segments are used for decisions that have a disparate impact on certain groups. Finally, an incorrect approach would be to use an evaluation metric that is not appropriate for the chosen clustering algorithm or the nature of the data. For example, using the Davies-Bouldin index without understanding its assumptions about cluster shapes might lead to a misinterpretation of cluster quality. This is professionally negligent as it demonstrates a lack of understanding of the evaluation tools, undermining the credibility of the analysis and potentially leading to the selection of a poorly performing model. This can have ethical implications if decisions based on such flawed evaluations lead to negative consequences for customers or the business. The professional decision-making process for similar situations should involve a clear understanding of the business problem, exploration of the data to understand its characteristics, selection of appropriate clustering algorithms based on these characteristics and the problem's goals, rigorous evaluation of the chosen algorithms using a suite of relevant metrics, and finally, interpretation of the results in the context of the business problem, with a focus on actionability and defensibility.